All right, so let's go through a quick example that kind of shows you how well this theory works. What I'm going to do is I'll try and calculate the viscosity of benzene at room temperature. So if we write out our formula for viscosity, it was Planck's constant times Avogadro's number times divided by the molar volume times e to the, and then for the energy barrier, I'll just use 0.41 times the enthalpy of vaporization, which I'll look up from a book, divided by kBT. So if I start writing those things out, Planck's constant is 6.626 joule seconds times Avogadro's number, 602 e to the 23 atoms per mole. I'll look up I can't look up the molar density, but I can look up the density of benzene, and I can use that plus the knowledge of the molecular weight of benzene to calculate the molar volume. And then I'll calculate the thing that's in the exponential by looking up the enthalpy of vaporization. And since that comes in joules per mole when I look it up online, rather than using kBT as the denominator, I'll use the universal gas constant times T, because kBT and the universal gas constant are actually the same thing, except for one's per molecule and one is per mole. So if I run through that calculation, I can calculate the theoretical viscosity as 0.732 e to the minus 3 Pascal seconds. How does that compare with experiments? Well, it's actually pretty darn good. So the experimental viscosity is 0.65 e to the minus 3 Pascal seconds, and so you're only off by like a little less than 20%. So that's pretty good considering how little work we just did. In practice, you won't always be that close, but typically you can get within about 50% for chemicals that have small molecules in them. So note that this does not work with large chain molecules, and definitely do not try using this with polymers.